Hello, my name is Robert Smith and I'm with New River Community College. Today we are looking at balancing redox reactions. This is essential in the study of electrochemistry and many other fields. And to do so, we follow a specific methodology. It is not entirely similar to uh, conducting a balanced chemical reaction or solving for a balanced chemical reaction. Um, so there's extra steps, and we will need to take those into account as we go forward. If you try to do a direct balancing and just assigning numbers or prefixes to coefficients to the different species at the outset, you're going to get the wrong answer. So please focus and take the time to actually do it out correctly. So there's two in redox reactions. We balance in either acid or base, and I have both types in this problem set. So we're going to start off with base, which is actually the harder of the two, and then we're going to do the acid, which has one less step than the base does. So let's get started. The first thing you want to do with a redox reaction is you want to break it up into its two half reactions. So you want to do the oxidation and the reduction reaction. So the oxidation looks like this, and the reduction looks like that. Now for the oxidation reaction, you'll note that there is an oxygen on the right-hand side of the reaction, but there's not one on the left-hand side. And in order to balance this, we'll have to account for that oxygen. And in order to do that, we add one water, so H2O. But now we have two hydrogens on the left-hand side and none on the right-hand side. The oxygens are now balanced, but we need to balance out the hydrogens. So we add two protons to the right-hand side. So now the number of hydrogens, oxygens, carbons, and nitrogens are all balanced. However, the charge is not balanced. You'll note that on the left-hand side, we have a -1 charge overall because water is neutral. But on the right-hand side, we have -1 from CNO, and then +1 from hydrogen and proton, and then there are two protons, so the overall charge is a +1. And in order to get this to be a truly balanced reaction, we need to add electrons to balance the charge. And you add electrons to the side that's more positive to make it look like the side that's of the equation that's more negative. So we'll have to add two electrons to the right-hand side. And now we can just double check. We have two hydrogens on both sides. We have one oxygen on both sides. We have one carbon on both sides, one nitrogen on both sides. And the charge on the left-hand side is -1. Charge on the right-hand side is -1 + 2 -2. So that gives us a -1 as well. We could do the same procedure on the reduction reaction, where we take, so let's see, we would take two waters on this side. So now our oxygens are balanced. We have 4 oxygens on either side. We have 1 manganese on either side. Now we have to account for the 4 protons. So there's 2 times 2. So 2 from the coefficient, and then 2 hydrogens per water. So we'll add 4 protons to this side, to the left-hand side. And now we need to look at the overall charge. On the right-hand side is neutral, and on the left-hand side is a +4 -1, so +3 overall. So we need to add 3 electrons. As a sort of sanity check, when you're doing these kinds of reactions, you may look and make sure that your electrons for the oxidation and reduction reactions are on opposite sides of the equation. If you find that you have your electrons both on the left-hand side or both on the right-hand side for either reaction, you know you made a mistake somewhere. So you'd have to go back and check and validate that you're doing it correctly. So now we want to add these two together. But in order to do that properly, we want to cancel out the electrons. We do not want electrons on both sides, on either side of the equation. So we're going to make them equal to one another. And the lowest common factor between 3 and 2 is 6. So we'll need to multiply the top equation by 3 and the bottom equation by 6. And I'm going to write out the whole equation. The bottom equation by 2. I'm going to write out the whole equation, and then we'll do some cancellations. So we have 3 waters plus 3 cyanides. And then from the top equation, we have 3CNO plus 6 protons plus 6 electrons. And then on the second equation, we end up with 6 electrons plus 8 protons plus 2 permanganates. Down to 2 manganese oxide. Okay, so now we can add these two equations together. Oops, there should be an oxygen here. And we cancel things out on either side. So as you're adding them, if you have 6 electrons on the left-hand side and 6 electrons on the right-hand side, then your net number of electrons in the end will be 0. Similarly, we have 6 protons and 8 protons on either side. So this actually becomes 2 protons. And we have 3 waters and 4 waters, so that just becomes 1 water. So those all canceled out in this process. So now once you've done your canceling, you can just add the two equations together. So we end up with 3 cyanides plus 2 protons plus 2 permanganate ions. And that goes to the product side. And I ran out of room, but okay, so this is balanced if we were doing it in acid, but we're asked to do it in base. So bear in mind, base in performing your equilibrium reaction or finding your equation, your overall redox reaction, a balanced redox reaction in base requires one extra step. And that is to make it so that for every proton that you have that's by itself, you add the same number of hydroxide ions. So to the left-hand side, we're going to add 2 hydroxides. And what you do to one side of the equation, you have to do to the other. So we're going to add 2 hydroxides to this side. So we're going to, the 2 hydroxides and the 2 protons will react to make water. So we end up with 3Cn minus plus 2H2O plus 2 permanganate, 3CNO plus 2MnO2 plus H2O plus 2OH minus. And you can maybe see what our next step is. We have 2 waters on the left-hand side and 1 water on the right-hand side. So we can cancel that with that. And we are left with our final balanced equation, which is 3Cn minus plus H2O plus 2MnO4 minus yields 3CnO minus plus 2MnO2 plus 2OH minus. So that is our balanced reaction in base. Let's look at another problem, very similar, but instead we are looking at the problem in acid. So here we have our chromate and oxalate ions and making chromium ion and carbon dioxide. So again, we're going to split up the reaction into two half reactions. So we have Cr2O7, 2 minus, goes to, and we should have 2 Cr3 plus, and we need the total, we need to balance out the oxygens. So we have 7 H2Os, which means on the other side, we're going to have 14 H pluses. And we'll balance the charge after we've done the second one. So let's do the second one. So we have C2O4, 2 minus, goes to CO2, but there's 2 carbons on the left, so we need to balance that first. So now we have 2 carbons on the left and 2 carbons on the right. We have 4 oxygens on the left and 4 oxygens on the right, so we don't need to add any waters to the second problem. So let's look at the charges. On the first equation, we have 14 plus 14 from the protons, and then minus 2 from the chromate. So we end up with plus 12 on the left-hand side. And on the right-hand side, we have 2 plus 3, so that's plus 6 overall on the right-hand side. So we need to add 6 electrons to make this balance, charge-wise. And then we need to look at our second equation. We have a minus 2 versus a plus 2, or a minus 2 versus neutral, so we need to add 2 electrons to balance the charge. So now the charges are balanced on both half reactions by themselves, but we want to combine these half reactions, so we're going to multiply this second equation by 3, making it so that it's 3 C2O4, 2 minus, yields 6 CO2s, plus 6 electrons. Again, we have 6 electrons, so that they're ready to add together for both equation 1 and equation 2. But the electrons are on opposite sides of the equation from reaction to half reaction to half reaction. So we know that we're doing this in the correct manner. So when you add those together, the electrons will cancel. That's the only thing that cancels. We don't have any protons or waters canceling in this one. So we end up with 14 H plus Cr2O7, 2 minus, plus 3 C2O4, 2 minus, yields 2 Cr3 plus 7 H2O plus 6 CO2. And this is a balanced reaction in acid. If we had this in base, we would then add 14 hydroxides to either side, and you'd end up with 14 waters on one side and 7 waters on the other. So the 7 waters would go away, and you'd end up with 7 waters on the left, and everything else on the left would be the same. And then on the right, you would have no water, but you would have 14 hydroxide ions on the right-hand side. So that would be in base. So base requires one extra step than acid, but otherwise in acid, this is all you have to do. Just count the total number of oxygens on either side. Whichever side is deficient in oxygens, you add that number of that number of waters to the side that's deficient. And then back on the original side that had enough ample oxygens, or have the initially higher number of oxygens, you add the twice the number of waters in terms of protons. So you add 2 times the amount of how many waters you had in protons. So in this case, we had 7 waters, so we added 14 protons. And then you simply do a charge balance by counting up the charge on the left-hand side, counting up the charge on the right-hand side, and whichever one has the higher charge, you figure out what the difference between the charges are, and you add that many electrons to the side that has the more positive charge. You do that for both reactions, and then you simply add them together and cancel out whatever species exist on both sides. And that's in acid. And then if you need to do it in base, you add whatever the net number of protons are. You to both sides, you add that same number of hydroxide ions. The protons react with the hydroxides to make water, so that should equal the same amount of waters on the side that had the protons. And then you cancel out any species that exist on both sides. Now that you have hydroxide on one and water on the other, you may have had water on the side that now has the hydroxide, and so those waters will cancel, and you'll be left with a reaction that has no protons, but excess hydroxides on the opposite side.